The definition you all wrote down. Of a vector space and examples of defining a particular vector space. That is, we're going to do some examples and we're going to see how it is that what we actually have to define in order to specify a vector space in those concrete examples. So first of all, recall a vector space. So I'm going to give definition 2, the one that enumerates the axioms, over a field F is a set, first of all, a set V with operations, that is functions, set functions from the Cartesian product of this set V with itself to another copy of V, which is called addition. This is the group operation for the additive abelian group. This is the addition of vectors. And a second operation, which we'll call times, which is called the field action or scalar multiplication. And it takes an element of the field and an element of the vector space and spits out another element of the vector space. So this one is the field action or scalar multiplication. And these two operations satisfy some axioms. Following axioms. And these are the names from the book. Okay, commutativity. And on your quiz and in general, I'm going to ask you always to qualify these statements, so be careful to do that. So we're going to say for all u and v, for all pairs of vectors u and v, adding u plus v and adding v plus u give me the same answer. That's the commutativity. The abelian part of the additive abelian group. Associativity, which is that for all, now we need 3 vectors, u, v, w, and v. U plus v plus w equals u plus v plus w, regardless of how we group them. And remember that says, in this one, I first add these 2 vectors to produce a new vector, then I combine it with that one. And doing it in the other order, first combining the last 2 vectors and then adding that to the first vector, whether I do it in either order, I get the same answer. So that's the associativity in the additive abelian group. And there was another axiom also called associativity, which had to do with the field action, with the scalar multiplication. And that said also for all u and v, and for all ab, which are in the field, ab v equals a bv. Okay, and again, the content of this is that on this side we have a field multiplication. So this is multiplication in the field, and then we have scalar multiplication. So one scalar multiplication happens over here. On this side we have 2 scalar multiplications. The b multiplies the v to produce a new vector, and the a multiplies the result of that. And the content of it is that those 2 operations give the same result. We have the additive identity axiom, which says that there exists a 0, a special vector in V, which regardless of what other vector I choose for all v and v, v plus 0 equals v equals 0 plus v. Okay, so it says this special vector works for all v as an additive identity, and because of the commutativity, I don't actually have to write both of these. Right? Okay. We have an additive inverse, which says that for all v in v, for every vector, it has an additive inverse, w in v, which once we feel confident it's unique, we can write as minus v. There exists a w in v such that v plus w equals 0. And here I'll omit the other order because we know that it's commutative. We have a multiplicative identity axiom. And that says for all v and v, when I take the 1 of the field and I scalar multiply v, I get back v. And finally, we have distributive properties. So for all a and b in my field, and for all u and v in v, we want two things to be true. First of all, if I were to add in the vector space, so a vector space addition, u plus v, and then scale by a, I get the same answer as if I scale each vector by a and then add in the vector space. Right? So this one has one scalar multiplication, this one has two scalar multiplications, and we require that we get the same vector as a result. The other axiom we want is that a plus b applied to a vector equals au plus bu. So this says if I take two elements of the field, a and b, and I add them together in the field and then apply them as a scalar multiplier of some u, I take the action, I get the same answer as if I apply the scalar multiplication twice and then add in the vector space. So those are our axioms for vector space. Okay, so today I listed those out in the version that doesn't really talk about groups. So let me tell you a word about the role of groups in this class. So you may feel from yesterday, if you don't like that sort of thing, that there was an infestation of groups. Like many things, the Germans have a compound word for that, and the word is Gruppenpest. So in the 20s, which means an infestation or plague of group theory, in the 20s, Eugene Wagner helped emphasize the formal role of group theory and representation theory, which is studying groups through linear algebra, in quantum mechanics. And some of his colleagues, other physicists at the time, felt that such crazy math had no place in physics and that we should stick to more concrete things. Foremost among them was Ernst Schrödinger, who referred to it as Gruppenpest and thought that it should be gotten rid of. But with time, it turned out that that perspective was really useful, and the bias was kind of reversed. And through the work of Hermann Weyl and others, group theory and representation theory was placed at the foundation of our understanding of many aspects of fundamental physics, including quantum and particle physics. In fact, it became so popular that it was trendy to call things groups even when they weren't. And group invariance in general became the key to unlock many aspects of physics. So, sometimes these abstractions feel a little awkward, but end up being quite useful. My aim here is not really to teach you much about group theory. You should have already seen a little bit of that in 311. But instead, to organize axioms, right? To give you a convenient abbreviation that might be easier to remember. In some sense, that's what makes it possible for humans to do math, is that we have kind of increasingly sophisticated definitions, increasing amounts of structure packed into definitions, and that enables us to keep moving instead of having to unpack everything. But I should say that it's not really necessary for you to think explicitly about groups or about such abstractions to understand this course. So when I say, and I won't say it that much, but when I say something like, let G be a group, you should feel free to instead think, write out the axioms. Let G be a set G with an operation, which is called the group operation. Let's call it star, usually called plus in this situation, G cross G to G, such that, well, for all G and H in G, G star H is also in G. That's kind of this closure property. It's not really needed because we have this definition of an operation that enforces it. sometimes people think of that as a property of groups, so I want to mention it. But we do need this associativity for all f, g, and h in G. F star g star h equals f star g star h. We want there to exist an identity element, which I'll call E for now, in G, such that for all G in G, it behaves as an identity. G times the identity equals G equals the identity times G. And finally, for all G in G, there exists an inverse H in G, which is either denoted minus H or H to the minus 1 in most of our examples, such that G times H is equal to the identity. It's equal to H times G. But since these axioms occur so frequently, it's convenient to organize them, or I find it convenient to organize them into a single word, a group, and you may not find it as convenient, and that's okay too. Don't mind if you unpack things. But you do need to know what a vector space is. Okay, some terminology and asides that I'd like to mention before we continue. I've mentioned some of these on Monday, but just to be clear about it. First of all, what do we say? So the definition of vector space contained a set, right, and a field and some relationship between them. And to indicate that, we say different things. We might say a vector space over the field, say over R. Right? I might write an abbreviation of this, vector space over R. This is almost a pun, right? But it's over. You can remember it that way. So I'll write sometimes a vector space over R. We might say a R vector space. Or we might say a real, spell it out, real vector space. Okay, all those mean the same thing. Just want to make that observation. Different ways of saying it that mean exactly the same thing. There's vector space, and this is the field that's associated to it. The other thing that we use different words for to mean the same thing is when we say V is in V, right? So what do we call this thing? Well, it's a vector, which is something in a vector space. We also call it sometimes an element of V. Thinking of V, this emphasizes sort of the vector spaceness. When I say it's an element, well, that sort of emphasizes the set structure, but we're just saying something in the set, something in the vector space. And if we want to emphasize the geometry, we might call it a point. So I say let V be a point in V. Again, there's no real distinction between these. They all mean the same thing. Okay? But you'll see all these words used. And the geometric thing is most useful when we're thinking about something like our vector space of arrows on the blackboard, in which case, well, this is like literally a point in space. Right? So I want to think geometrically, we use the word point. And again, the warning about thinking geometrically, I encourage you to do it. It makes a lot of properties intuitively obvious. It emphasizes the fact that a vector space is not the basis that we've chosen. It's not the list of numbers, but something more fundamental. But warning, this sort of 2D, 3D intuition. So we live in approximately real three-dimensional space, and our intuition of that is great for some things, but sometimes it can lead us astray. And we'll see specific examples of that later in the class, especially when we're considering infinite dimensional vector spaces, and we're considering finite fields and things like that. And even when we're considering the complex numbers, because the complex numbers, it's sort of like 2D, but it's somehow complex. But actually, it's four-dimensional, and so we're already out of dimensions, right? But you can do not too badly thinking about real space and kind of letting warning buzzers go off in your head when you get near special properties of 2 or 3-dimensional real space. So with time, I hope that intuition will start to become helpful for you. Okay, so for most of the rest of today, what I want to talk about is some specific examples of vector spaces and how we define their key operations, their structure operations of addition, the group operation, the additive abelian group operation, and the scalar multiplication. Okay, so examples. Okay. So here's the simplest example. I can take a set with one element and think of it as a vector space. In other words, I claim that over any field, there is a vector space V such that the cardinality of that vector space as a set is 1. There's exactly one element in it. So what is that element? What should I call it? Identity. Right. So one of the axioms of the vector space is that the 0 vector is in V. Okay? And if you look at it closely, that's the only axiom that really forces a particular element to be in it. Inverses have to be in there, but they all depend on some other element. Right? The only thing that's sort of not quantified is that there has to be a 0 in the V. And so if it's one element, that's got to be our element. So in this case, this is finite vector space. Right? It only has one element. So we can do things like write out its addition table. Okay? If I take 0 vector and I add it to the 0 vector in this space, what do I get? I get the 0 vector. What if I have a field element alpha and I multiply alpha times 0? I get the 0 element. That's right. Okay. So we know how to do addition. We know how to do scalar multiplication. Everything's very boring, but you can check that all the axioms are satisfied. It's a legitimate vector space. Okay. Over any field. So that's the first example. Our second example is a little bit more complicated. So think about the interval 0, 1. That is, I have a real number line. I have 0 and I have 1. I'll look at all the points in between those. And then I want to think about functions. Functions, real valued functions on that interval. Functions f from 0, 1 to the real numbers. And I would like to make this set, the set of all functions from 0, 1 to r into a vector space. Okay, it's going to be a vector space over R. So suppose I have a function f that goes from this interval to R. You know, I can think about these as I can draw a picture. Here's 0, here's 1, and here's a function. It doesn't have to be continuous, you know. Doesn't have to, it can be incredibly badly behaved. F, here's another function g. Let's maybe make it straight, constant function. How do I add them? What should f plus g look like? Any ideas? I heard something. Someone has an idea. It's okay. We can fix it if it's not perfect. So if I wanted to say there is some other function f plus g, let's make f simpler. Suppose f looks like that. Let's make it even simpler. Let's start at 0. So this is f, and that's g. What should f plus g look like? Got it? Hump up here, right? So what are we doing there? We're looking at each point x on the number line, and we're saying what is f of x, and what is g of x? Those are two real numbers, and we're just adding them together to get f plus g, f of x plus g of x. It's kind of a pointwise addition. Right? So that's a good definition, right? We say we have these two things, f and g, they're just functions from 0, 1 to r. They have no other structure. We just have a set of these things. We want to add two of them together. And what we do is define that addition by defining a new function. A new function which we're going to call f plus g. And to define a function from 0, 1 to r, all I have to do is tell you if I give you any point x between 0 and 1, what is f plus g of x? Right? If I tell you that, for all x in 0, 1, then I've told you what this function must be. And as you suggested, that definition is f of x plus g of x. So what's going on here? On this side, we are defining addition in the vector space. We're defining it by defining a new function. But to define a new function, I say what it does on each point x in its domain. And we're doing it in terms of addition in the field, addition in R. Right? So over here, we said that f of x and g of x were functions to the real numbers. We know how to add two real numbers. Just add them. And so we define f plus g of x to be f of x plus g of x. So over here is addition in R. Over here we're defining addition in V. How about scalar multiplication? Suppose alpha is a real number, and f is a function from 0, 1 to r. And I would like to define the scalar, the field element alpha, times the function f. How should I do that? Do it analogously to what we did over there. I think I heard an idea somewhere in this direction. Yeah, exactly. Again, we're going to do the same thing, right? So we take a point x, evaluate it. Now we just have a real number, f of x, right? And then we can just, it's a real number, and we have another real number, alpha, and we know how to multiply two real numbers. So we do that, and we get a new real number, right? So the right way to write this is alpha f. So we're defining alpha f. We're defining scalar multiplication. Alpha f applied to x is defined to be alpha applied to f of x. Or this is multiplication in R. So that's our addition. That's our scalar multiplication. This is the first example of something we'll see lots of times in this class, and lots of times in mathematics, which is that when you have a bunch of functions to something else, that induces a lot of the structure of the domain onto the set of functions. Right? We use what we knew about real numbers, how to multiply and add, to define how to multiply and add, scalar multiply and add in the function. Okay. Another example, and this one's going to be a little bit imprecise right now. So I said that if I had two vector spaces, u and v, there was some notion of a transformation between them, a function between them, which preserve the properties of the vector space. We'll get into that next week. The right kind of transformation to think about is something called a linear transformation, which is basically just one that preserves the properties. Commutes with vector space addition and scalar multiplication. And it turns out that the linear transformations, let's say linear transformations, let's say between, for concreteness, finite dimensional vector space. If I have two finite dimensional vector spaces, I could take the set of all linear transformations between them. It turns out that itself is a vector space. And the way you make it into a vector space is not so different than the way we made this into a vector space. Right? We know there's a vector space going on somewhere, and so that gives us a clue as to how to add and scalar multiply. Right? Okay, so there's a reason I chose these three examples, because these three examples are not lists of numbers. So if you've seen some vectors and some matrices in a previous class, they were often lists of numbers. And these things, I want you to note that a vector is not, at least not necessarily, a list of numbers. You know, x, y, z, whatever. A vector space, similarly, is not necessarily a set of the form of this form. You know, all x, y such that x is in the field and y is in the field. Certainly that's an example of a vector space, but as we've seen, not all vector spaces have that structure. And lastly, and this won't become quite clear till later, a linear transformation is not the same thing as a matrix. So, you know, a matrix does define a linear transformation once we know what we're talking about. This is, to me, one of the most important things about what makes this course different from other courses that you've taken in linear algebra is that we're going to understand what a linear transformation is without thinking about it as a matrix. So use that as a tool, but not as a crutch. Okay. So let's give another example that's more familiar. An example that is all these things, that is a list of numbers, and where transformations are matrices. That's an important example we'll need for lots of things. So that's Fn is the notation we use. And this just means ordered n tuples of field elements. With element-wise or point-wise addition, and something we might call broadcast scalar multiplication. What do I mean by that? Well, if I have a list of numbers, x1, x2, x3, I could think of that as a function. Right? I could think of this as a vector, as a function that goes from the set 1, 2, 3 to the field. And that's not so different from the function we just saw that went from the interval. And I can do the same trick. I could think about, what is the point-wise? So the points here are just 1, 2, or 3. So to add two of these together, I say, x1, x2, x3 is one such vector or one such function. y1, y2, y3 is another such function. And I'm defining their sum, defining the sum in the vector space in terms of the sum of the points. x1 plus y1, here are the entries, or the elements. x2 plus y2, x3 plus y3. So that's what I mean by element-wise, or entry-wise would maybe be a better word. And we know how to do this part because these are just field elements. Right? So this is addition in the field. So we've used addition in the field to define addition of vectors when we have n tuples of elements. But you could imagine that there's maybe some other definition of addition we could have used. It's a particular choice. And there'll be twists on this that we'll see. And then to get scalar multiplication, we have to broadcast it. So in other words, we're going to take alpha times x1, x2, x3. We could think about it as 3 copies of alpha, 1 applied to each of those, and then just run the field multiplication. So this will be the definition. Alpha x1, alpha x2, and alpha x3. Right. So we've defined now our scalar multiplication in terms of element-wise or entry-wise or point-wise multiplication in the field. Okay. Questions? Okay, so in the last 10 minutes, I'm going to give one more example, sort of intermediate between these. So one of the examples we saw was uncountably infinite dimensional. Right? It was this huge space of functions from the interval of real numbers between 0 and 1 to real numbers. That's a huge space. Then we saw finite dimensional stuff like this, where there's only a few field elements needed to parameterize it. We haven't quite defined what we mean by dimensional, but you can get some idea. It's how many real numbers, how many numbers do I have to specify? How many parameters are there? So let's do one that's intermediate that has countable infinity of dimensions. So let's define what we're talking about as a set first. We'll define a set of things, a set of univariate polynomials, so-called because one thing varies. Polynomials. Univariate polynomial, and let's think about this as a function, is a function from f over a field to f, which has a particular form, which I can specify in a certain way. Now, this cuts down the possible functions a lot. given by P applied to a point x, which is an element of the field, is equal to A0, some constant. A0 is in F, plus A1x. A1 is in F, plus A2 x squared, plus A3 x cubed, and so on, up to some highest finite number, A sub m, x to the m. Now this m, the largest integer, positive integer that appears in this expansion, which is not 0, where the am is not 0, is called the degree of the polynomial. So what we're saying here, the qualifier is for some A0, A1, Am in F. And this list is finite, because I chose a particular endpoint, not allowing infinitely many non-zero coefficients. OK, so that's what I mean by a polynomial. It's a certain kind of function. So suppose I have two of these now. P and Q are polynomials. For example, maybe P, take an example, e.g. P of x is, say, 3x squared plus 1, and Q of x is x to the fourth plus 2x cubed plus 5x squared. Just some choices, but we want to know what happens in general. And now we need to make this into a vector space. We have to define. It's just a set right now. Right now it's just a set. And you forget whatever you know, what else you know about polynomials. So far it's just a set of functions from the field to the field. And the set is specified by saying it has this form, and the ai's are allowed to vary, and the m is allowed to vary. So it's some giant set of things. And I want to define how to add them. P plus Q. How should I define the polynomial P plus Q? It's very similar to last time. We define it point-wise by looking at elements of F, right? We define P plus Q. We're defining the addition in the vector space. P plus Q applied to x is defined to be P of x plus Q of x. So here we're defining addition in the vector space in terms of addition in the field. For every point x in the field, for every element of the field, I define a new function, P plus Q, that goes from the field to the field by taking the original function's values and adding at x and adding them together. And similarly, I can define scalar multiplication. If A is a field element, I can say that AP, this new vector, this new univariate polynomial, this new function from F to F, I can define that by looking at what it does on each value, giving you a new function by defining what it does on each value. And I can do, again, just use the field multiplication. Okay, so defining of scalar multiplication. And here we have field multiplication. And so in our example, of course, P plus Q would be of x would be x to the fourth plus 2x cubed plus 8x squared plus 1. And one way we could compute this is by thinking of each P and Q is defined in terms of such an addition, breaking it up and then using this rule repeatedly, right, on each degree. And over here we have, say something like 7 times P of x is equal to 21x squared plus 7. So what's the additive identity in this vector space? Zero. We're always going to call it 0, right? But 0 is the 0 polynomial. Right? With the 0 function, different ways of expressing that. As a function, it's the function at 0. This is going to look kind of funny. 0, because it's a polynomial, I can call it, right? I can think of it as applying to something. 0 of x is equal to 0 in the field. 0 in the vector space of polynomials. It's a space of polynomials. It's a space of functions. I can apply it to x. That's equal to 0 no matter what I use as the input. That's one way of saying what the 0 thing is. It's the 0 function. By the way, that's the 0 vector of the other vector space we were talking about before too, right? But we could also say it's the polynomial with each coefficient equal to the 0 in the field. For every I look at, all of these chosen field elements are all 0, so that when I add kind of element-wise or point-wise the coefficients of each of the exponents, I always am adding a 0. OK, so that's all for today. On Friday, we'll talk about subspaces.